Hello guys and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at a radiation problem, and in this case it's a radiation problem of a gray surface. So, attention must be paid when we have a gray surface because it's obviously not that idealized black body, which simplifies things a lot. So in this case, the problem statement reads, a hemispherical cavity of radius zero point 0.1 meters has emissivity of 0.5 and is at a temperature of 137 degrees Celsius. If the surrounding environment is at a temperature of 300 Kelvin, determine the net heat flux leaving the surface of the cavity, assuming the cavity to be a gray diffuse surface. B. If the cavity is cylindrical with a diameter of 0.2 meters and a height of 0.1 meters, what will be the net heat flow? And C. Compare the results with that of a black surfaced body, or cavity, I should say. Okay, so first thing to note is that this guy is not in Kelvin, and we know that radiation needs Kelvin, so we're going to have to convert that one there. Second thing to note is, well, I already said that it gave the hint that this was not a black body, but then here it says it is a gray diffuse body. Why is the diffuse important? Because it means that if it's a diffuse surface, gray diffuse surface, it means we can use reciprocity, right? Reciprocity to be able to find shape factors and view factors, etc. So that's a good hint there of what we need to do. What are we looking for? On part A, we're asked to find the net heat flux. Okay, so that is lowercase q. Let's put it over here, running out of space. Lowercase q in watts per meter squared. In B, we're asked to find what is the net heat flow. So that is uppercase Q, net, and that will be in watts. And then on C, we're asked to compare the result. And I'm not so sure from the wording of the question, I'm not sure if we should compare it to the hemisphere or to the cylinder. I'm not sure. So we're going to do both just to play on the safe side. Okay, well, this is the drawing that we're given. This is the hemisphere here. And then there's the opening here. If we were to draw this 3D, obviously this would be something like this. So there's an opening there. This guy here would have an area of pi r squared, right? Note that they're giving us, once again, they're just repeating what they said in the statement. The emissivity is 0.5, but they're giving the emissivity of surface 2, right, which is an imaginary surface, which is the one I just drew. Should not have eliminated that. Should probably keep this here. An imaginary surface here, surface 2, which is, the opening of this hemisphere. And knowing that this has an emissivity of 1 is quite an important information, because then it says pretty much we can treat this imaginary surface as a black body. Okay, so the temperature of the environment, T infinity, is given as 300 Kelvin, straightforward. And T1 from surface 1, that is, and this is also T of 2, right? Because 2 is just an imaginary surface of the environment. And T1 is 137 degrees Celsius. So we sum that to 273, we get 410 Kelvin. Okay, so what I know before I do any sort of math is that energy is leaving the net energy transfer, Q net, is leaving my surface 1 and going towards surface 2. The other thing I know is that all the surface of this cavity is emitting energy, right? So therefore, part of the energy will indeed reach surface 2, but part of the energy will go to the cavity itself, right? So the cavity sees itself, in other words. Mathematically, the way we say that is that the view factor, the shape factor of surface 1 when it sees itself is not 0, right? So it does have a number there. So I already see that in this problem, I'm going to be using shape factors when we need to find shape factors to be able to solve, okay? If I'm interested in the net heat flux, what I know already is that the net heat flux is going to be from 1 to 2, right? Because of this, I know that 1 is warmer, hotter than 2. So therefore, that I'm looking for this, right? And if I want the flux, I'm going to be looking for this, okay? And the last thing to note is that this is not a black body, right? So if we go and apply our beautiful equation, the shape factor of 1 to 2, Stefan-Boltzmann constant, area of 1, T1 to the 4th minus T2 to the 4th, this is going to be incorrect because this is not a black body, right? So we can't apply the simplified version of the equation. Also, we cannot apply the same, let me go ahead and copy this, we cannot apply the same equation if we just put the emissivity here of 1, right? Why is that? Because this would be the case of a gray body that's not receiving any sort of energy, right? If it's just a gray body emitting energy, then this is a simplified version, and that's be all good. We put that's only half of it is being emitted, all good. And it's not the case because a gray body is also receiving energy from this surface too, right? From the environment, because the environment is at 300, so it's also emitting radiation to the gray body. So this is also not okay. I'm going to use the general one. Okay, so what we're interested in is the general form, and then we can simplify to the situation that we have. General form, let's write it down. Let's write it in green. Well, it's the general form. Well, general form between going from 1 to 2, right, will be the radiosity of 1 minus the radiosity of 2. Remembering that radiosity is the total energy leaving the body, so it takes into account energy being reflected plus energy being emitted. And then we need to account for both the surface resistance, which is the 1 minus emissivity of 1, divided by area of 1, emissivity of 1, right? Surface resistance of surface 1 plus the space resistance, right, which is between the space between the two surfaces, and there's going to be area of 1 shape factor 1 to 2, view factor of 1 to 2, plus once again we have another surface resistance at this time for surface 2 to area 2. Okay, so this will be our general equation here for this case. Radiosity you can easily transform into just Stefan-Boltzmann times the temperature to the fourth. And the other thing here that we can simplify is this guy here, right? Because they say quite clearly that the emissivity of surface 2 is 1. And you know that if this is 1, then this thing here is 0. If this thing goes to 0, then the whole thing goes to 0, right? We didn't need to know this per se to be able to do that step. If you think about it, right, the area of 2 is fixed, but the area of the environment, let's think of it this way, the area of infinity to infinity tends to infinity, so therefore this area will be very large going towards tending to infinity, which would mean this guy would tend to 0. So even if they didn't give away the emissivity and say like, hey, treat that surface, imaginary surface 2 as a black body, we could have still applied this idea here. Okay, so what happens here with this equation, and this is what happens. 1, 2, radiosity, I'm just going to transform into Stefan-Boltzmann's constant, T1 to the fourth minus T2 to the fourth, then divided by, this is kept, this part is kept, we lose, this is stupid, there you go, we lose this part here, which goes to 0 as we saw. Now, one thing interesting here is that we have now area 1 multiplying both sides, so we could easily remove, area 1 from here. We can choose area 1 that is multiplying, let me move it here, multiplying both guys, and that means I can just send the area up there, multiplying. Right, so this would be further simplified too. I'm going to do this. I'm going to copy this whole thing here and just multiply by the area. Like this, and then like this, and then just multiply by area 1. Which, again, makes it my life easy because if I'm looking for the heat flux, all I need to do is ignore that area there, right? Because the area is going to be divided, or let's do the whole thing nicely so that nobody gets lost. If I divide everything by area, both sides by area 1, I'm going to get the same thing as heat flux from 1 to 2, which will simply be this guy here. Yeah, so that means that as long as I have my constant, which I do, the temperatures, which I do, the emissivity of surface 1, which I do, and the shape factor, or the view factor, which I don't, I can calculate the heat flux. All right, so the question now is, what is the shape factors? Okay, so let's do that. So I have a copy of the picture here for us to do it. All right, what's the idea? The idea is the energy that leaves the surface, all right, either sees surface 2, the imaginary surface 2, or sees surface 1, sees itself. Right? There's no other option here for the energy leaving surface 1. So if I sum up surface 1 plus surface 2, that has to be 100%. No other options. All right? What else? If I look at surface 2, right, and looking at the, what will be the energy being emitted by surface 2 into this imaginary space here, right? It's imaginary down there. Surface 2 only emits energy, surface 2 only emits energy to surface 1, right? All the energy being emitted by surface 2 sees surface 1. And surface 2 would be a flat surface, right? It would be a disk, a flat disk. So we know that the amount of shape factor of F22, how much surface 2 see itself, is 0, right? No. So once again, I can do, okay, so that's the case, then all the energy leaving surface 1 going to surface 1, leaving surface 2 going to surface 1 is 100% or 1. And what I can do now is I can relate these two guys here by reciprocity, right? So if I can relate F1, 2, and F21 by reciprocity, then I can use this equation here to solve for F11, right? I don't even need F11, but just for the sake of it. What does reciprocity say? Reciprocity says, let's put one more equation down here. Reciprocity says that amount that 1 sees 2 times the area of 1 has to be equal to amount that 2 sees 1 times the area of 2. And again, we can only do this because the question clearly says this can be treated as a gray diffuse body, right? If my F21 is 1, then my F12 will simply be area of 2 divided by area of 1. Right, so now just need, and then times F21, which is 1, so this guy goes away, 1. Right, so I just need the ratio of the areas to be able to find what is F12. Area of this guy, this is quite simple. This is just pi r squared. Pi r squared. This is surface 2, so let's put a subscript 2 there for that. So this is my area 2. And area of this guy here, it's the area of a sphere, but only have half a sphere, hemisphere, so therefore this half of the area of a sphere, right? So area 1 will be 4 pi r squared. This is r1, so surface 1. And we're going to divide that because we only have half a sphere. So therefore, what we're interested in is pi r1 squared. Note that conveniently, the radius, right? So the radius of the sphere and the radius of this circle here are exactly the same. So r1 and r2 are both 0.1, right? The diameter is 0.2, so the radius is 0.1. So that's very convenient. So that means that if I go over here, all I'm doing this here is pi r squared, so 2, and here I have 2 pi r squared. This is r1. However, the two r's are the same. Pi is a constant, the same. So this conveniently becomes 1/2. Okay, so that means that the shape factor, how much surface 1, let's go back to our original thing. The amount that leaves surface 1 and goes to surface 2 is about half of the emission of this surface here. The other half actually goes back to itself, right? So it goes back to the cavity itself. All right? Brilliant. So now if this is 1/2, then this becomes trivial here. We can now put these things here. So that's going to be 5.67 times 10 to the minus 8. Here we have 410 to the 4th. This is 300 to the 4th divided by 1 minus 0.5 divided by 0.5, and this is just going to be 1. Oops, plus 1/2, which is just 2. So that's just going to be 3 in the bottom. And on purpose, I'm going to leave the numerator and the denominator separate here. So I'm going to do 1143, which is just this multiplication here. And on the bottom there, I'm going to have 1 plus 2, which is 3, which gives me about, what are you here? 381. 381. And that is watts per meter squared because I haven't multiplied by the area. And that will be our answer for part A. Okay? And then you probably noticed that I left this on purpose because what is going to change now that I have a cylinder is just the bottom part there. So that's going to simplify my life a bit. Okay, so this is part A. Instead of part A, let's look at part B. So part B, we now have a cylinder, a fat cylinder, something like this. What was the, so the height of the cylinder is 0.1. And the diameter of the cylinder is 0.2. Okay, so we have sort of fat cylinder. And then we have, again, we're going to call this surface 1. And the opening here is what we're going to call surface 2. Again, this is a circle. Okay. this imaginary surface. Everything is the same, right? So this is still, this is still 410. T infinity is still 300. Those things did not change. What does change is obviously the shape factor, because now this area of the cylinder changed, right? So the area A1 now is different, and the shape factor, we would expect it to be different too. In respect to this, nothing changed, right? So it's still a flat surface there. So, surface number 2 does not see itself. That didn't change. What else? This didn't change as well. This is still surface 2 does not see itself. Surface 2, area 2 is still the same. No, that our radius is still the same, it's still 0.1. But what does change is area 2, right? Or area 1, I should say. Area 1. Because now area 1 is a cylinder, so we have the bottom of the cylinder, which is going to be exactly the same thing, right? So just this part here, pi r squared. So pi r squared, so r1, plus the side of the cylinder, which we know to be 2 pi r, the circumference times the height, right? So 2 pi r1 times the height, or L. No, let's put L. You're used to using L there for length. Let's use L now, or H if you want. R1. This guy is 0.1. This guy is also 0.1. So conveniently, this is the same as r squared. Okay, so we can rewrite this as 3. So it's going to have 2 plus 1 here. So it's going to be 3 times whatever we have there. So it's going to be 3 pi r squared, or 3 times 0.1 if you want, meter squared. That will be our area 1 there, right? Okay, so now when we go to do the ratio of the areas, the top area is still the same, pi r squared. The bottom area has changed, and now it's 3 pi r squared. So this is also convenient. We're just left with 1/3 here. Okay, so, and this, makes intuitive sense, because in a cylinder, I hope it makes intuitive sense. In a cylinder, the cylinder sees itself more than the hemisphere would. Okay, so in other words, there is the 2/3 of all the energy being emitted by this cylinder actually goes back to the cylinder, whilst 1/3 of the energy emitted by the cylinder goes to surface 2, to the outside of the cylinder cavity, or the cylindrical cavity, I should say. Okay, about 1/3. So what's going to change? Well, what's going to change is this point here, nothing changes. Or, oh, we need to find, well, I'm going to keep it this way, and then I'm going to go and find, because we need to find net heat, right? Not heat flux this time. I'm going to keep this. Okay, so let's see. This is the same, this is the same, this is the same emissivity, all good. This now is 1/3, and that's the difference, right? So this becomes 1/3. Everything else is the same, and that's why I left, this top part here, because what's going to change that bottom part? This is still 1, and this now becomes 3. So this becomes 1 plus 3 equals 4. And this is 1/4. And then it's going to be 1143 divided by 4, which is about 285.754. So let's go ahead and approximate that. We'll go ahead and approximate that to 286. Okay, but this is not the answer, right? Because, like I said, we're not after heat flux. We're in reality after the net heat transfer. So we just need to multiply that by our area. Area 1 in this case is this guy here, and all good there. Let's go ahead and do that. So I'm multiplying my 286. Actually, I multiplied 285.75, and I'm multiplying that by 3 pi 0.1 squared. Why is this not squared? It's supposed to be squared. Squared. Which gives me about 26.93. Let's go ahead and approximate that to 27. And now it's watts, not watts per square meter, because we're multiplying by square meters. So this is the answer for part B of the problem. Cool. All right. So what else? What are we missing? Part C asks us to compare. And like I said, it's not clear to me whether we're supposed to compare the hemisphere cavity or the cylindrical cavity. So let's do both, just to play safe. Okay, so if we're comparing with the hemisphere, what we're comparing there is, okay, my Q from 1 to 2. In the first case, if this is a black body now, what do we need? What changes? Well, now, if you remember, if it's a black body, not a gray body anymore, then we can use this analysis, right? The simple one. This analysis here. So Q12 becomes, let's see how close my handwriting matches up. It's just this guy. So in this case, Q12 will just be my V factor for the hemisphere, which is half times my constant, 5.67, 10 to the minus 8. Area 1, I forget what area 1 was, half the sphere, right? So 2 pi r squared, and this r was 0.1. And then here again, 410 to the fourth minus 300 to the fourth. If we disregard, or actually if we divide everything by the area and we calculate the flux, which I think is going to be more convenient because we have the flux on the other one, we get this to be 571.5 watts per meter squared. Okay, so what I did is I divided both sides by this. So instead of calculating the 2 pi 0.1 squared, I divided both sides by that so that I have heat flux. And now this allows us to compare the two, right? Because we had, if you recall, where's my calculation? Here it is. So if you recall, this part here is going to be the same for both, right? Obviously. And then what changes in reality is this bottom part here. And this bottom part here is the 1/3. Okay, so in one case, we're multiplying the top part by 1/3. In this bottom case, you know what? I'm going to rewrite this so that it makes more intuitive sense. Let me rewrite this. Let me divide by the area so that it's nice and everything makes sense. I'm going to have 1/2 of this T1 to the fourth minus T2 to the fourth. Okay, now again, this we know to be the 1143 I found before, right? And this is just 1/2. In the case of the gray body, this was 1/3 instead of 1/2. Okay, so in other words, what I can do is, okay, if I want to do a comparison, I can do, okay, what is the energy being emitted by the gray body in respect to how much energy was being emitted by the black body? And obviously this component here is going to be canceled out on both of them, and we're going to be left with the 1/3 here on the gray body divided by the 1/2 here on the black body. And this is simply put 2/3, right? And this, I think this is a good comparison to make. So what we're saying here is that the gray body emits about 2/3 the energy that it would if it were a black body, right? And then for the cylinder, we're going to do very similar analysis. This time I'm going to go straight into, try to do straight to the point. So cylinder. What we have there, if I want to do Q12, is the same thing, right? View factor from 1 to 2 times Stephan Boltzmann times T1 fourth, T2 to the fourth, and then area 1. If I divide everything by the area, I'm going to get the flux, which will simply be 1/3, which is the view factor for the cylinder, times Stephan Boltzmann's constant, T1 to the fourth minus T2 to the fourth. This guy is the 1143 you found before. And if I want to do a comparison between the gray body and the black body, here on the black body, I'm going to have 1/3 on the bottom there, 1/3 on the bottom there. And if you recall, what we had on the gray body was 1/4. Here it is. Right, we have 1/4 there. So simply put, this is 3/4. Right, so in the case of, if we're comparing with the hemisphere cavity, then the gray body emits 2/3 that of what a black body would. And if we're talking about the cavity, the cylindrical cavity, then the gray body emits 3/4 or 3/4 that the black body would. So if the cavity were a black body, it would emit more energy. If it's a gray body, it doesn't emit all the energy, so it emits only 3/4 of it. All right, so I hope this was useful. Hope this helped you out. If it did, consider giving a like. If you have any questions, just leave them down below as per usual. And if not, we'll talk soon.